introduction about my group. So my group started in November 2013, and these are my current members. And we are mostly working on lithium-ion battery and monovalent lithium, sodium, and potassium, and multivalent minor activity on aqueous zinc and batteries. And for that, we are mostly working on the oxide material and polymeric acid material. So for the students, I just want to briefly go through. We have this evolution of battery, which is a very, very long process. So it started in 250 BC with Baghdad battery and so on, which is really wonderful. Then we all know there are different kind of, voltaic pile and so on. Various European scientists, they contributed to the Daniel cell and a lot of things. Pretty much, you take a jar, you put two dissimilar metal, put some electrolyte or some solution, you get some EMF potential difference and try to use it. Very simple. Either it's one set of metal or a series of metal, that's how you can make a cell, or a series of cell, battery, and so on. So this is the important point, 1859, when there was a concept of this lead acid battery. And I was working in University of Picardie, Jules Verne, with Professor Tarascan for 2 years. That time, Jules Verne has a lot of scientific literature, and he mentioned like in future people will use lead acid battery and battery-driven vehicle, and it was before 200 years so he predicted, and it is true. And lead today also it works for different kind of application. Then there is a development of carbon zinc or Lakeland cell, and also we have different kind of cell. And then finally, to get more efficiency, people came up with this nickel-cadmium battery. But now cadmium is toxic and carcinogenic, so the government don't allow that. So from cadmium, people move to nickel metal hydride battery, and then there is iron-based Edison battery and alkaline and so on. And the lithium metal was discovered in 1850s. But then from 1912 onwards, there were a lot of research on lithium-based compound, and in 1970s actually it picked up with Professor Goodenough and other people. The concept of intercalation came in 1970s, and a lot of electrode material came in 1980s, and in 1991, lithium-ion battery was commercialized. And we all are grateful to these three handsome gentlemen. Professor Stan Whittingham for having the concept of intercalation. Professor John Goodenough simply being good enough, and to make different kind of electrolyte, both oxide as well as polymeric based, and Professor Atria University to have the petroleum coke based anode material for safe battery operation. Okay, so when we talk about the battery materials, essentially we have something called rocking chair or intercalation system. So what it does is basically we have some cathode material and anode material. It's like a husband and wife. So cathode material has some alkali element. Alkali element are somebody who can move in and out of the structure without destroying the structure. And the iron moves inside the battery through a separator with electrolyte. So inside the battery, we can call it as an ionic conducting device, and outside the electron move, it is an electronic device. Yeah? So ionics, electronics, everything is involved. And essentially, when we talk about the chemical potential of cathode and anode, the difference with that, we can actually get the cell operating potential, and our overall tendency is to get high energy density. Basically, that's a multiplication of the operating potential and capacity. So how much discharge capacity you can get repeatedly, and how much potential, at what potential you can get. Either one parameter or both parameters if you increase, you can get high energy density. Now, coming to the materials perspective, we all know about the lithium battery. The problem with lithium battery is the abundance is very low. So earlier nobody was using, that's okay, but now there is a huge amount of use. Because of the low abundance, the cost of lithium carbonate is very high. The cost of lithium metal also is very high. So as a result, the cost of the battery can become very high. The good part is low atomic mass and high voltage, so very, very high energy density. Now, in some segment, at least where there is no need for any gravimetric, volumetric consideration, we can go for post-lithium battery like sodium-ion battery. Here again the atomic mass is a little heavier, voltage is intermediate, 0.3 volt less. As a result, what happens, the energy density is low, but the abundance of sodium and the uniform distribution is very, very high. As a result, what happens is we can get low cost of sodium carbonate, sodium hydroxide, as well as low cost of sodium metal, and in principle you can design some economic battery. Now in sodium, one advantage of India is, if we say sodium-based chemicals, so the number one company in the world is Tata Chemicals, but most of them, they make pesticide, fertilizer, sodium bicarbonate, baking soda, all these things. So these are low and low profit margin chemicals, but if we can do something on sodium-based electrode also, sodium-based precursor, Tata Chemicals can take lead and it is possible to do. Now, this is the concept why we are going for sodium battery as a post-lithium chemistry. Now, when we talk about the battery material, any cathode material, essentially we can say there is an alkali element, lithium or post-lithium, sodium, potassium, so on. We have a transition metal which changes the redox state, cobalt, nickel, iron, manganese, and so on. And we have either oxygen to form oxide cathode or one extra anion called polyanion. So this is the classic composition, and here I am talking about the A, which can be either lithium or post-lithium like sodium battery. Now, main thing when you go to the industry for any battery materials, essentially the first point any company people talk about is cost benefit analysis. For academician, the money is citations and H index, but for the company it is real dollar. So here, if we see any battery pack for an automotive vehicle, so there is basically a battery pack with good BMS. So this consists of individual 18650 cells. Now, if we take each cell and try to again do an analysis, so this cathode account for around 50% cost of the battery, then there is manufacturing cost, electrolyte, and so on. So this is the main culprit here, cathode. And also there, it consists of lithium and some critical metal like cobalt, nickel, and so on. So now Australia and all different countries, they are calling graphite, cobalt, nickel, and lithium as critical minerals, and it is really possible, it will be wonderful if people can recycle and use it again and again. Yep. So here, the point is, these are also distributed very non-uniformly, so there are different problems here. Now, when we talk about the lithium, sodium, and potassium, granted the size of lithium is small. Sodium is bigger, potassium is bigger, but if we see the solvation sphere, the stroke radius, the sodium and potassium, because of the high electropositivity, all these things, they can be smaller. As a result, what happens, the stroke radius can be small, and it is possible that they also can intercalate nicely. And this is typically the lithium-ion battery and sodium-ion battery, because the sodium voltage is low, so we can say there is some minus 20% less energy density, but the cost per kilowatt hour can be very, very good. Now, this is all about the material perspective in challenge, and also just from fundamental perspective, everybody talk about cationic redox. So this is like the classical thinking, cationic redox. That when we have a layer structure where the transition metal which changes the redox without changing the position, and that leads to the capacity here. But now also there is a concept called anionic redox, where in addition to the cation here, also the oxygen, the anion also can take part at high voltage in some redox activity. As a result, we can combine the capacity contribution from cationic as well as anionic to get in principle very, very high capacity. Now, one good thing is, with cation plus anion capacity, the capacity is very high. And also, anionic redox happens invariably at high voltage. So, in principle, we are getting high voltage and high capacity. Too good to be true. But in real life, it is not that easy. So, here, the point is, when we go to the high voltage, there is a problem with the crystal structure stability and so on. So, because of the stability, what happens? after some time there is a degradation of the capacity. There's a big problem. So if you change the voltage in you cut off at 4, 4.1, 4.2, 4.3 at different volt, accordingly you will trigger different amount of anionic redox. Accordingly the capacity will go, but the cycling stability will go down. Yeah. Capacity increase, cycling, so there is a balance between the capacity stability. So what will be the real cut-off voltage by BMS, where we can get little better than cationic plus anionic capacity. Anyway, these are different concepts. So the whole respect for this anionic redox we can give to one person, Professor Jean Roxel from France. So he was the first person in 1970s when Professor Whittingham did the work on the titanium bisulfide, all this thing with the lithium intercalation and so on, the titanium redox, cationic redox. Around 5 years or 10 years later, he was using the same chalcogenide, titanium bisulfide, to show the sulfur anionic redox. Very, very early work, and he has a lot of single author papers, and he was a routine visitor to SSCU in IISc Bengaluru. So here what we mentioned that it is possible that when we have the chalcogenide like a sulfide, it is also possible that before the titanium redox happens, sometimes there is a band overlap, the sulfur can take part in the redox mechanism. And later, just like from Whittingham to Budanov, some sulfide to oxide, to increase the voltage, people try to move from the sulfide of John oxide to different kind of lithium-rich oxide and so on, and they found there is possibility of showing oxygen anionic redox. And then there has been various proofs by wonderful high-resolution TEM, XPS, and so on, and also some theoretical analysis. So pretty much, when we have some lithium-rich system, in one case when there is no lithium-rich, one side there is only lithium, one side there is transition metal. When there is lithium-rich, transition metal are less, and there are more lithium. As a result, the local bonding environment is different, and we can get some different electrochemical property. Now, when we have this transition metal and all, so basically the cationic redox, the transition metal change, oxygen change is different. In case of anionic redox, there is a band overlap. As a result, before the transition metal, some oxygen redox can also occur. So with this kind of basic understanding, I want to show you one classic case study of sodium-based oxide material for anionic redox. So I want to describe one P2 kind of cobalt sodium ion battery cathode material to discuss their synthesis, crystal structure, and some anionic redox activity and the effect of rate kinetics on the activity. Now, when we charge and discharge very fast in a moderate rate or very slow, how the anionic redox change, I will try to show that. Again, going back to Professor John Roxel, so he classified all the oxide material into two different, in a map like this. So pretty much this is the cationic radius, lithium, sodium, potassium, rubidium, cesium, all kind of things. Slowly it is getting bigger and bigger. And this line, it shows basically the electronegativity of the AA bonding, alkali and oxygen bond and metal oxygen bond. There is a function. So if we put all kind of oxide, pretty much it follows, there is a kind of a 45-degree line. Anything that go above that, it has P kind of structure, prismatic. Anything below that has O kind of structure. So this was like a universal map, and this is true for even potassium-based oxide and so on. Yeah? These are sodium-based oxide, potassium-based oxide, lithium-based oxide. Everything will follow the same thing. So what are the P and O? So all kind of oxide, essentially, we can denote by Professor Claude Delmas notation, which is basically either it is O type or P type. What is that? In case of O type, the sodium exists in a coordination of octahedra. So if you take the sodium and put the nearest neighbor oxygen, it will look like an octahedra. Yeah? And in case of P type, if you take the sodium and you take the nearest neighbor oxygen in the top and bottom layer, it looks like a prism. So here is the octahedra, there is a prism. That is the P and O. And the number here, basically notice after how many layers it repeats again. So this is A, B, C, A, B, C, A, B. After 1, 2, 3 layers, again A, B repeats A, B. A, B, A, C, A, B, A, C. After 2 layers, 1, 2, again A, B repeats. So that's for 2. So that's why it is P2, P3, O2, O3. Among them, if I just tell as a fluid language, what is the octahedra? In octahedra, basically the two transition metal blue layer, they are looking away from each other. Because of that, the interlayer distance is low. In case of prismatic, they are exactly on the top of each other, 3 oxygen, 3 oxygen. Oxygen repulsion is very high. That's why the interlayer distance is slightly higher. When this distance is slightly higher, more opening, then the sodium can move in and out very, very fast. So the rate kinetics in case of prismatic system in general is much better than A kind of system. So basically, because the interlayer distance is high, activation barrier is very low, so ion mobility is very, very high. That's why people try to move for this P kind of system, P3, P2. In real life, it is very difficult to make P3 kind of system. Many compositions are known for P2. So we will talk about this P2 system. So we designed one new composition called Na0.7, Mn0.6, nickel, cobalt, O2. So we all know about the system called Na0.7, MnO2. So rather than 100% manganese, we try to dope some nickel and cobalt to get this new composition. So this is made very easily by different nickel acetate, manganese acetate, cobalt acetate in stoichiometric ratio we put, and we have some oxalic acid. When heat and stir and get the excess water out, we can get some intermediate complex, and when we heat that at 900 degrees for 3 hours in air, we can get this phase 12 material. So this is the synchrotron XID we have done at Thailand synchrotron CM14, and there you can see complete very high intensity nice peak, all correspond to the P2 kind of system, the classical system, and we have some secondary failure about 2-8%, which is basically some kind of nickel oxide, which is very, very stable and we cannot avoid it. So this is a phase 12 material, and you can see this is the structure. Again, this is the P2 kind layered structure. So in the transition metal, rather than only manganese, we have manganese, nickel, cobalt. Mostly it is manganese, and this is the sodium, so which is sitting in the P2 prismatic kind of site, and so on. Yeah, so here the interlayer distance is very, very high, so sodium can move easily. And when we see the elemental distribution, so this is sodium, cobalt, nickel, oxygen, or manganese, everything is uniformly distributed, and we can get some nice HRTM pattern with very, very good electron and the interlayer distance and so on. So essentially, we can say we have got this co-precipitation synthesis of the phase pure P2 type material, and it has a hexagonal structure with this symmetry, and overall it has a micrometric particle also with hexagonal morphology. Now, this material, without any optimization, when we did some half cell study, so initially we limit the voltage up to 4 volt only. When the voltage is low, only the cationic activity works. So there we can get some nice activity here, so which is basically because of the transition metal, the cationic redox. Now, if we go to little high voltage, if we hit up to 4.5 volt, then what happens is, in addition to the cationic activity, also we get some extra peak, which is because of the oxygen or anionic redox activity. Okay. Now, this is the liquid DV curve. Now, if we just sweep the cyclic voltammetry towards higher and higher voltage, later we can actually capture each and everything and the anionic redox also. And also we can see that with GITT and so on. So this is again, depending on the voltage window, we are getting only cationic or cationic plus anionic. So as a result, we can see with wider potential window, we are getting the observation of both cationic as well as anionic redox base to get some high capacity. Now, what happens when we have this material? This is a P2 kind of system, as I mentioned. This is the initial pristine material, and when we charge to very high voltage, then what happens? All the sodium go out, and because of that, the oxygen there is a huge coulombic repulsion, and the interlayer distance increases, and it remains P2, but because of the huge change, we can call something called P.2. It's like a distorted version of P2, and as a result, what happens? You can see the peak shifts towards the lower angle. Lower angle basically means high interplanar distance, and when the sodium come back again it goes back to the similar P2 structure. Yeah? Again it goes back. So it's a reversible phase transformation of P2 to P.2. This is like a biphasic phase transformation. And when we do the PITT study, that's a potential static intermission titration technique, then what happens during the cationic redox, the peaks are very close to each other. It's like a single phase redox. But in case of the anionic, you can say they are very far from, which is basically a biphasic redox. Yeah? So single phasic cationic redox and biphasic anionic redox. This biphasic is nothing but this P2 P.2 phase. So in principle again, throughout this process up to this, the P2 structure remains intact, and here it becomes P.2, sudden change in expansion, again come back and so on. So the anionic redox here, we wanted to probe further. So we did some in situ Raman spectroscopy. So in Raman, actually when we do some anionic redox, when there is a peroxo bond formation at high voltage, this is the low voltage, peroxo is not there, at high voltage where the anionic redox is happening, we get some peroxo bond, again upon discharging, again they disappear, again it comes back to normal. So with this we see, with Raman study we saw some reversible formation of peroxo OO species which is easily captured, and also we did some XPS analysis in IISc. Now the XPS is a surface technique, but in IISc we have the machines where we can etch it and do XPS, again etch it further, do it, so it's kind of 50 millimeter something you can etch and you can create the bulk also. So there after about 100 millimeter etching something, when we do that, then we can see during the charging and discharging, we see the typical nickel 2 plus 3 plus 4 plus, the nickel redox, cationic redox. In addition, also we see the oxygen redox here. Yeah? So basically this peak, the change that we are seeing is because of the peroxo bond formation and oxygen redox. So we can say that with XPS we see nickel cationic redox as well as the oxygen redox couple. Both we can capture by both Raman spectroscopy as well as the in situ Raman and ex situ XPS. Now with the help of Professor Bangladesh at IISc Korea, we did some DFT calculation. So these are basically the initial structure at different perspectives, you can see, and upon desodiation, different degree of desodiation, they stabilize different structure, and they find that pretty much, it is like they are getting this kind of final composition, and so the final composition is this, and sometimes some vacancies are there also in the transition metal side. Occasionally there is some vacancy. When there is a vacancy, again there will be problem with the local electron structure can change. So these are different structure, and they can, in fact, by DFT calculation, they can predict the voltage profile. They also get the cationic as well as the anionic redox, which is matching well with the experimental data. And when they did the battle charge calculation and the transition metal charge calculation, they can see we are indeed getting the nickel redox at a different degree of sodiation. The nickel is active and cobalt redox is happening, and the manganese doesn't change much. Yeah? So the manganese is same. Most of the activity is coming because of nickel and some amount from cobalt. And when we go to high degree of desodiation, indeed they can see oxygen redox is coming. Yeah? This is all because of the magnetic charge of oxygen, and you can see it is seriously changing. So this is a wonderful proof from theory that there is anionic redox. And if there is a hole in the transition metal, or if there is no hole, accordingly, we can see the local band gap, everything changes. And in principle, we can say from DFT also there is observation of both cationic redox with the nickel cobalt and anionic redox. Now cobalt is only 10%. Yeah, so the activity, the capacity contribution is very little. Most capacity comes because of the nickel and oxygen. Now one reason is why we put cobalt 10%, because cobalt is known to give some structural stability and cycling stability. That's the reason why we are putting small amount. Okay, now coming back to even more crystallography study. So this is our typical voltage profile with low voltage cationic, mostly nickel, and high voltage anionic redox. Now, at this particular point, so around 0.33, some other 33% when the reaction is happening, we see a sudden change. This plateau is very, very well known for different kind of layered oxide material. In case of sodium cobalt oxide, we see a lot of strip-wise profile. There is a sudden strip around this, and which is basically because of the observation of superstructure peak. So here, if you see, these are the 111, there is a small amount of new peak, 112 and 113. These are the typical superstructure peak which appears by close observation, and this is the typical our P2 kind material. So this is corresponds to some, even if there is the orthorhombic structure, there is a superstructure peak with this kind of dimension, and which is very, very similar to different NOx-CO2 kind of system. Mini-layered system has the same thing. Now in Austria, we did some in situ X-ray diffraction for this material, and in situ X-ray diffraction also you can see there is an observation of faint superstructure peak. So maybe it may not be clear, but here you see during charge at a particular point there are some new peak appearing. These are the superstructure peak, and also these points we see some extra peak, very feeble, small intense peak. These are the superstructure peak. And in general you can see when we are going from as a charge, discharge, you can see there is a sudden, there is a gradual change and coming back, change and coming back. This shows like a different kind of phase transformation. Now, it is possible in many oxide materials. When you go to high volt, it changes from P2 to O2. Once the prismatic become octahedral, it is irreversible, it will not come back, the cyclic stability will be bad. So you want to avoid this P2 to O2 or P2 to OP4. No O, only P. So in our case, luckily we are not getting any O2 kind of phase. So there is no peak because of the O2, only it is P2 and P double point 2. So P2 or sudden change in the length, interference distance P2. So we are avoiding this O2 kind of phase formation, which is good for us. Now we did this kind of in situ XRD study for different rate. So I want to show you some example. So this is the in situ XRD study done at C by 20, the typical C by 20 rate. So during the charge, discharge, so basically you can see the sodium content is decreasing, increasing. That is very well known. Now, during the process, you can see how the P2 phase is decreasing, then again increasing like that. And here also P2 phase, like how it increase, decrease. Now, in this case, you can see in some case the P double point 2 is not forming at all. Yeah? So in case of C by 20, it is only P2 kind of phase and the ABC parameter change continuously and something is going on. But in case of C by 10, when we do the charge discharge little rapidly, then what happens? So this is the voltage profile, the blue one. This is desodiation, sodiation and so on. You can see the P2 phase amount is increasing, decreasing, but around this composition you can see there is a sudden appearance of P double point 2 like that. Yeah. So pretty much at high rate we can see there is a P2 as well as the P double point 2. In the low rate we don't have any P double point 2. Single phase, double phase. So there are two kind of reaction. So this is P2 initial phase, the interplanar distance is this much. When the sodium is getting out, desodiation, then what happens? The oxygen they repel each other. So as a result the interplanar distance can go from 5.3 to 7.1 angstrom. This is the P double point 2. What we say schematically, initially we have this transition metal, these are the sodium. When you take it out, this transition metal layer, all this oxygen, they try to repel and they become P double point 2. So this is the piston, this is this. So initially, at the surface, when the sodium will go out, in the surface there will be like P double point 2 phase formation. In the bulk there will be still P2, so there will be a two-phase reaction mechanism. Now I want to summarize all kind of thing we do. So when we do the charge discharge of this anionic material at very slow rate, C by 50, at very slow rate, yeah, C by 50. So this is C by 50. Then what happens? We saw this is our initial piston P2. You see the large peak, P double point 2 peak is here, two dotted line. So when we do C by 50, all the P2 became P double point 2. Okay? So all P2 became P double point 2 here. Okay? So pretty much when we do C by 50, there is a biphasic transition from P2 to P double point 2. 100% transition from P2 to P double point 2. Now when we do the same thing at C by 20, this is C by 28, charge discharge, when we do the P2 remains P2. Okay? So in the C by 20, P2 remains P2, just little bit change because of the interplanar distance, slight change, but P2 remains P2, there is no P double point 2 peak here. So what we feel at C by 20, there is no phase transition, it is a single phase P2 that remains. Now the interesting point is when we do at C by 10, at C by 10 what happens? We have the observation of P2 as well as the P double point 2, you see? P2 and P double point 2, like that. So initially if I just do the charge discharge, we are getting some amount of P double point 2, and if I do at high voltage, if I do CCCV, keep for a long time, slowly everything will become P double point 2. It is decreasing, increasing. So what happens is, here we have a coexistence of P2 and P double point 2 domain, just as it was shown here, like a P2, P double point 2, it shows like that. So with this, I want to conclude that we found that P2, P double point 2 phase transition is kinetic or rate dependent. So it is not only the phase is changing, also it matters the degree of phase changes, how fast or slow you are charging. So to summarize my talk, we we are talking about the anionic redox, oxygen redox. For that we came up with this new composition derived from Na0.7 MnO2 by substitution of nickel and cobalt. Nickel basically gives to high cationic potential, that's why, and cobalt 10% gives some structural stability, cycling stability. So this material we found the observation of 4.1 volt anionic redox at very high voltage, which is reversible. And when we do the dense analysis, so we found during the charge discharge, there is no oxygen evolution. This is very important. In many anionic redox, some oxygen evolved. So initially we are getting first two cycle some CO2 CO because of the electrolyte decomposition. But if you see the red curve here, throughout the first three cycles, there is no oxygen. So dense analysis, no oxygen evolution. So the anionic redox is happening, but oxygen is not coming out. It is inside the system and it is reversible, which is a good thing. And we don't see any change from P2 to O2, but we see the change of P2 to P development to phase transition, and we find this phase transition is rate dependent. So depending on how fast or slow we charge, either we will have just P2 monophasic or fully biphasic P2 development or mixture of both phase. So with this, I want to conclude that this kind of anionic redox material are rate dependent. So we don't have to use it at a very high rate, we have to use at slow rate. So I want to acknowledge my funding bodies and mostly the Humboldt Foundation for last 3 years. It was very helpful. And also I want to thank my collaborator, Professor Stephen Trinberger from IISc Austria, Professor Danghua Seth from KAIST South Korea, and Professor Prashant Naik and Professor Max Prisoner, my host of KIT. And Maria is with us. I could not resist that I want to stop this with this slide. With this young man, some people who define, they will remain forever. And I really like this sentence by him, that be enthusiastic about life, be grateful for life, and be thankful to people who like to engage in meaningful dialogues with you. With this, I would like to conclude, and I'll be happy to take any questions. Thank you.